Tonight, we are going to enter a region of the universe so large that, on the first maps, an entire expected population of galaxies seemed to disappear. Not one galaxy, not one cluster, a broad interval of space where the graph should have been crowded, but was almost blank. This is the Boötes Void, one of the most famous underdense regions ever discovered. It is often described as an enormous hole in the universe, a place hundreds of millions of light years across where almost nothing exists. Some accounts call it too large to be real. Others suggest it is a wound in the cosmic web, a sign that modern cosmology has missed something fundamental, or a darkness so complete that the few galaxies inside it have become islands beyond any meaningful neighborhood. The truth is more careful than that. It is also more disturbing. By the end of tonight, you're going to understand how astronomers discovered the Boötes Void from missing points on a redshift graph, how they reconstructed its three-dimensional scale, why ordinary gravity can create an enormous region containing so few bright galaxies, what later radio observations actually found inside it, whether modern cosmology can produce structures this extreme, and why explaining the void does not make it feel smaller. Before we get started, if you love exploring the depths of space, please like this video, subscribe to Calm Space, and leave a comment telling us where in the world you are listening from tonight. Now, let's begin. The story did not begin with a photograph of darkness. It began with spectra. In the late 1970s and early 1980s, Robert Kirshner, Augustus Oemler Jr., Paul Schechter, and Stephen Schechtman were measuring the redshifts of galaxies in several narrow fields of sky toward the constellation Boötes. A galaxy's light carries patterns produced by atoms in its stars and gas. When those patterns are shifted toward longer, redder wavelengths, astronomers can estimate how rapidly the galaxy is receding as the universe expands. For nearby cosmic structures, redshift becomes a practical distance marker. It is not a perfect ruler. Galaxies also have their own motions, and the conversion depends on the assumed expansion rate. But with enough spectra, the method turns a flat patch of sky into something closer to a depth map. The team measured redshifts for 133 galaxies across 3 fields. Then they plotted the results. The galaxies did not appear evenly distributed. They gathered into concentrations, as expected. But between those concentrations lay an interval of roughly 6,000 kilometers per second in recession velocity, where only one galaxy appeared. That gap was the first shock. Imagine recording the addresses of houses along several roads leading away from you. For a while, the addresses continue normally. Then, across every road, the houses almost stop. The empty stretch begins at a similar distance in each direction and ends at a similar distance farther out. At first, you might suspect the survey. Perhaps the telescope missed faint galaxies. Perhaps dust blocked the view. Perhaps the fields crossed an unlucky arrangement that only looked empty from Earth. Perhaps the chosen galaxies were poor traces of what was really there. Those possibilities had to be tested because a void is discovered through absence. A galaxy cluster announces itself with light. A void asks astronomers to prove that the missing light is not simply missing data. The original result was striking because the deficit appeared in more than one direction and over a broad redshift interval. The researchers estimated that the underdense region occupied about 1 million cubic megaparsecs under the cosmological assumptions they used at the time. The title of their 1981 paper carried a question mark: 1 million cubic megaparsec void in Boötes? That punctuation mattered. They had found evidence for something enormous, but the first map was still sparse. 3 narrow fields could pass through the same large structure, or they could pass through several smaller gaps that only seemed connected. The universe had provided a disturbing pattern. It had not yet provided the full shape. Even so, the gap immediately changed the emotional meaning of the galaxy map. Before large redshift surveys, photographs of the night sky encouraged a simple intuition. Galaxies seemed scattered through space. Some areas were richer, some poorer, but the large-scale universe was often imagined as roughly uniform, once the view became wide enough. The Boötes measurements suggested something more architectural. Matter was not merely clumpy on the scale of galaxies and clusters. Entire regions could be deficient. The missing population could extend farther than the structures human beings had learned to call enormous. This was not a literal hole in space-time. The word void has a precise astronomical meaning. It refers to a volume whose matter density, or whose density of chosen traces, such as bright galaxies, falls well below the cosmic average. Space remains there. Light crosses it. Gravity still acts. Dark matter, diffuse gas, radiation, and some galaxies can remain inside. The void is defined by shortage, not absolute nothingness. That distinction should reduce the mystery, but it creates another one. If the region is not a hole, then the missing galaxies require a history. Why did so few large luminous systems form there? Did matter leave? Did the surrounding structures pull it away? Did the earliest universe begin with a tiny imbalance that later grew into something hundreds of millions of light years wide? Those questions could not be answered from the first graph alone. First, astronomers had to determine whether the gap had real breadth across the sky. A single line of sight can exaggerate emptiness. A large spherical underdensity should reveal itself across many neighbouring directions, with its near and far edges shifting in a coherent way as the survey moves away from the centre. So the team went back. More fields were selected. More galaxy spectra were measured. One redshift at a time. The blank interval was tested from different angles. The first result also arrived at a moment when the scale of the cosmic web was still being uncovered. Astronomers already knew about clusters and superclusters, but the full foam-like organisation of galaxies had not yet been mapped across the immense volumes available to later surveys. A gap this broad did not fit comfortably inside the intuitive picture of galaxies scattered around an average background. It suggested that the background itself had structure. That was why the question mark in the paper title carried genuine weight. The team could have been seeing a statistical accident, a selection effect, or the first cross-section through something much larger. Each possibility implied a different next step. More exposure time would not be enough. The survey needed breadth. There was also a practical tension hidden behind the clean final graph. Some spectra were weak. A galaxy selected from a photographic plate might not yield a reliable redshift on the first attempt. Night sky emission had to be removed. Wavelength calibration had to remain stable. A misplaced line identification could move one point to the wrong distance. The credibility of the gap therefore came from repetition. Different galaxies, different fields, the same broad shortage. The pattern survived the ordinary ways a small survey could fail. The first discovery had been a missing population on a graph. Now the absence had to become geography. The follow-up survey spread across 283 fields and produced 239 new galaxy redshifts in and around the suspected region. Compared with modern catalogues containing millions of objects, the sample was tiny. In the early 1980s, however, each redshift demanded telescope time, a usable spectrum, careful calibration, and individual analysis. The scientists were not pressing a button and receiving a finished three-dimensional universe. They were assembling depth from narrow beams. A telescope pointed at one field collected light from galaxies that appeared close together on the sky. Their redshifts revealed that some were relatively near, while others lay much farther away. The telescope moved to another field. The process repeated. Gradually, the collection of sightlines began to outline where the galaxy population thickened and where it nearly vanished. The deficit persisted. The easiest way to picture the evidence is as a row of narrow windows cut through the same distant volume. In the central windows, the empty interval extended across a broad span of redshift. Shift the telescope sideways, and the interval shortened, as though the sightline were moving away from the middle of a large, rounded region. Shift farther, and ordinary galaxy counts returned. No single window proved the geometry. Together, they constrained it. The team also had to understand which galaxies were eligible for the survey. A magnitude-limited catalogue naturally loses faint objects with distance. If that fading selection were responsible for the gap, the shortage should continue or worsen smoothly toward larger redshift. Instead, galaxies reappeared beyond the interval. The survey could detect objects at greater distances than the void's far side, which made a simple sensitivity cutoff an inadequate explanation. Clustering complicated the graph in the opposite direction. Galaxies naturally gather into peaks and leave smaller gaps between them. The challenge was deciding when a gap became too wide and too coherent to treat as ordinary spacing. Its repetition across neighbouring fields supplied that evidence. Each spectrum was only one distance estimate. Together they formed a three-dimensional argument. Foreground galaxies, a broad, underpopulated middle, background galaxies, and the same sequence across a significant area of sky. Across neighbouring directions, galaxies became scarce over a similar range of recession velocities. The region was not perfectly empty, and it was not a clean sphere. Real structure is irregular, yet the broad pattern was coherent enough for the researchers to describe a roughly spherical underdensity centered near a recession velocity of about 15,500 kilometers per second. Under the distance scale used in those early studies, the inferred radius was roughly 62 megaparsecs. That historical number is often repeated as though astronomers found a solid cosmic bubble with a measured wall. They did not. The estimate came from galaxy positions reconstructed in redshift space. Redshift includes the smooth expansion of the universe and the galaxy's own local motion. A galaxy falling toward a cluster can appear displaced along our line of sight. Galaxies near a void can move outward relative to the underdense center. Those motions stretch or compress the apparent structure. The expansion rate used to convert recession velocity into distance also matters. Early papers commonly used a different value for the Hubble constant from the values preferred today. Change that assumed scale and the distance assigned to the same redshift changes. So the 62 megaparsec radius should be understood as a historical reconstruction, not a border carved into space. But the conclusion did not depend on the last decimal place. The underdensity was vast. The follow-up measurements also showed why the word spherical must be handled gently. Astronomers often use a sphere because a radius is easy to communicate and compare. The actual galaxy distribution around Boötes included walls, filaments, concentrations, gaps, and internal structure. A useful sphere can describe the scale without reproducing every contour. Think of placing a transparent ball inside a mountain valley. The ball can approximate the valley's overall size, even though the slopes are irregular and the floor contains ridges, streams, and isolated hills. For Boötes, the ball captured the shock. There was a broad volume where the number of bright galaxies fell dramatically below what surrounding regions suggested should be present. The deficit appeared across multiple sightlines. It had a near side and a far side in redshift. It occupied enough angular width that the first narrow fields were not merely threading an accidental gap. The missing population had become three-dimensional. That result also revealed something about the limits of perception. On an ordinary photograph, a distant void does not appear as a black disk. The sky in front of it contains foreground stars and galaxies. Objects behind it still send light through it. The region overlaps other structures in projection. Only when astronomers add distance information does the underdensity emerge. Without redshifts, near and far galaxies collapse onto the same flat image. With redshifts, the layers separate. A galaxy that seems to lie inside the same patch of sky may sit far in front of the void. Another may lie behind it. A few may actually inhabit the low-density interior. The void is not visible because the sky becomes dark in that direction. It is visible because a three-dimensional census reveals that too few galaxies occupy a particular depth. That is why this discovery was more than a curious empty patch. It was evidence that the large-scale universe possesses structure beyond what the eye can recognize directly. The map had walls and cavities. Galaxies gathered into connected regions, leaving enormous volumes relatively poor. The surveys were still incomplete. Fainter galaxies might remain undetected. Gas-rich systems could hide from optical selection. The interior might contain loose groups or thin filaments too weak for the early catalogue to reveal. None of those possibilities erased the central fact Adding more sightlines did not fill the gap. It gave the gap a shape. And once the shape became credible, the next question was unavoidable. What does a radius of 62 megaparsecs actually mean? The three-dimensional confirmation also changed the next scientific task. The question was no longer whether one narrow beam had crossed an accidental gap. Astronomers could begin asking what physical history produces an underdensity of this breadth, how it connects to surrounding structures, and whether its size fits any plausible model of cosmic growth. Before those mechanisms could be judged, however, the geometry had to be translated out of megaparsecs and into consequences a human mind could feel. A radius is easy to print in a paper. The time light needs to cross it, the number of galactic disks it could contain, and the impossibility of communication across it reveal what the measurement actually means. Astronomical language can make enormous distances sound strangely small. A megaparsec becomes one compact word. 62 becomes one manageable number. The mind reads the phrase and moves on. The geometry also contained a clue that the result was not merely a narrow tunnel pointing away from Earth. As the fields moved across the sky, the redshift interval associated with the shortage changed in the way expected when sightlines cut different chords through one broad underdensity. A field near the projected centre sampled a longer path through the sparse region. Fields farther away crossed shorter portions or missed the deepest interior. This was still an approximation. The sparse data could not trace every indentation, and galaxies do not mark density continuously. Yet coherence across direction and distance is exactly what transforms a line-of-sight gap into a three-dimensional candidate. The follow-up also made the surrounding concentrations important. A void cannot be measured only from its interior. Astronomers need the return of galaxies on the near side, the far side, and across neighbouring directions. Those richer zones act like reference marks around a pale shape. Their positions help establish that the deficit occupies a bounded region, rather than continuing indefinitely beyond the survey. This is why the follow-up survey carried more evidential weight than a simple increase in sample size. It tested the spatial pattern implied by the first result. A random fluctuation might produce one empty sightline. A coherent underdensity should influence many adjacent sightlines in a related way. The observations increasingly favoured the second possibility, even though the exact contour remained rough. The void was not inferred from one missing clump, but from the organised return of structure around a large deficit. So the confirmation did not consist of finding nothing again. It consisted of finding the structure around the nothing in the right places. That subtle difference matters. Absence alone is ambiguous. Absence organised by surrounding evidence becomes a physical feature. But the number is where the disturbing scale begins. 1 parsec is about 3.26 light years. 1 megaparsec is 1 million parsecs. 62 megaparsecs correspond to a little more than 200 million light years. That is the radius. The historical diameter approaches 400 million light years. Light itself, travelling at nearly 300,000 kilometres every second, would need roughly 400 million years to cross from one side of that diameter to the other. When the light began its journey, complex life on Earth was still moving through eras unimaginably distant from the present human world. Continents occupied different arrangements, forests, oceans, and animal lineages followed histories that had not yet produced anything like modern civilization. The beam would cross the void while entire biological worlds appeared and vanished. Now compare the diameter with the Milky Way. Our galaxy is roughly 100,000 light-years across, depending on which component and boundary is being measured. Place Milky Way-sized disks edge to edge across the historical Boötes diameter, and you could fit about 4,000 of them. 4,000 galaxies touching rim to rim. Real galaxies would not touch, of course. They would be separated by enormous distances. The comparison is useful because it converts one abstract void into a corridor measured in galactic bodies. Voyager 1, the most distant human-made object, is still only light-hours away. At its present speed, 1 light-year would take tens of thousands of years. Crossing Boötes is beyond every practical meaning of travel. Even messages cannot make the region feel connected. A light signal sent across the full historical diameter would arrive hundreds of millions of years later. A reply would require the same span again. Communication across that scale is not conversation. It is geology carried by photons. The sender and receiver would not share a civilization, a species, or perhaps even a planet in recognizable form. Yet the Boötes Void is not remarkable because it contains one completely empty straight line of that length. Its geometry is rough. Galaxies exist within it. Smaller structures interrupt the scarcity. The emotional scale comes from the volume over which the average population remains low. A lonely volume is harder to imagine than one isolated point. Stand on an island and the ocean extends around you. But the ocean itself contains water, currents, life, weather, and vessels. The void contains matter as well, though far less of it in the forms early surveys could see. Its isolation is not a perfect absence. It is a reduction sustained across a volume large enough to hold thousands of familiar galaxies. That difference matters because popular illustrations often turn the void into a smooth black ball. A clean sphere makes the scale visible, but it can also mislead. There is no black surface. There is no central darkness with a sharp edge. There is only a transition from a very sparse interior toward richer walls and filaments. If you cross the boundary, no instrument would flash at one exact moment. The galaxy density would change gradually. The surrounding gravitational environment would change. The probability of encountering a massive neighbour would rise. From inside one of the few galaxies, the void might not be obvious until an astronomer mapped distances far beyond the local stellar sky. This creates two perspectives that seem contradictory, but are both true. At the human scale, 400 million light-years feels like absolute isolation. At the cosmological scale, the region remains one feature inside a web far larger than itself. The universe contains structures spanning billions of light-years in connected arrangements. Boötes is vast enough to exceed intuition, yet it does not approach the size of the observable universe. It is not an edge. It is not outside the cosmic pattern. It is one of the pattern's deep depressions, and this is where the scale becomes causal rather than merely impressive. A volume this large cannot be explained by a recent local accident. No ordinary explosion could clear it. No single galaxy, cluster, or black hole could control matter across the entire region. The light crossing time alone tells us that the underdensity must belong to the slow history of large-scale structure. The void did not appear yesterday. Its roots reach back toward the early universe, when the matter distribution was nearly smooth, and the future cosmic web existed only as faint differences in density. The volume makes the scale even harder to hold. A sphere with a radius near 62 megaparsecs contains on the order of 1,000,000 cubic megaparsecs, which is why the original description used that extraordinary phrase. A cube, only 1 megaparsec on a side, is already large enough to contain millions of light-years of separation. The Boötes estimate gathers roughly 1,000,000 such cubes into one underdense region. Volume grows faster than diameter. Double the radius of a sphere and the volume becomes 8 times larger. This is why a void that is merely several times wider than another can contain a vastly greater amount of space. The emotional impression created by a two-dimensional circle understates what the third dimension adds. The scale also changes what counts as a neighbour. In the local group, the Milky Way and Andromeda are separated by about 2.5 million light-years and remain gravitationally connected. Inside a region hundreds of millions of light-years across, many local group-sized separations could be placed between the few major luminous systems. No traveller would experience the whole void. No observer could look across it in real time. Every complete image is reconstructed from ancient light arriving from different distances. The map is a mosaic of different pasts assembled into one present-day model. Nothing ate the galaxies. The more disturbing possibility is that, across most of this immense volume, many of those galaxies never formed in the first place. That possibility removes the most dramatic false explanations before they have a chance to grow. There is no evidence that a colossal black hole swept the region clean. A black hole's gravity does not erase matter across hundreds of millions of light years. Even the most massive black holes known occupy the centers of galaxies and influence their immediate surroundings most strongly. They can drive energetic outflows, heat gas, and affect star formation within a host galaxy or group. They cannot pull a mature population of thousands of widely separated galaxies into one invisible center without leaving an unmistakable gravitational structure. No such center appears in Boötes. The galaxies around the void do not orbit a hidden devourer. Light passing through the region does not reveal the lensing pattern of one impossible mass. There is no central object whose gravity could account for the deficit. An explosion fails for a similar reason. Explosions move through existing material. They create shells, shocks, heated gas, and debris. To clear a volume near the historical Boötes scale after galaxies had formed would require an event beyond known astrophysical energies, operating coherently across a region whose diameter light itself needs hundreds of millions of years to cross. The expected aftermath is absent. There is no expanding wall produced by one central blast. No uniform hot shell encloses an evacuated interior. The surrounding structures belong to the cosmic web, not to the wreckage of a single event. Dust cannot hide the galaxies either. Interstellar dust within the Milky Way can obscure portions of the distant sky, and astronomers account for that when selecting survey fields. But dust would dim objects along a direction from Earth. It would not create a consistent deficit over a specific redshift range, while allowing nearer and farther galaxies in the same direction to remain visible. The redshift structure defeats the illusion. A tear in spacetime is unnecessary. So is a collision with another universe, an engineered exclusion zone, or a flaw in a computer simulation. Those ideas can be attached to any dark illustration because they are visually flexible. They do not explain the measured distribution better than ordinary structure formation, and they do not make distinct, successful predictions for the data. Science does not reject them because they sound strange. It rejects them because the evidence does not need them. There is one more image to remove, and it is subtler. The Boötes Void was not a normal region filled with mature galaxies that later drifted away, like people leaving an abandoned city. Galaxies are not small particles that can be evacuated easily from such a volume. Once a massive galaxy forms inside a dark matter halo, moving the entire system hundreds of millions of light years requires an organized gravitational history far larger than any local disturbance. Void formation works earlier. The shortage reaches back to the conditions from which galaxies grew. Some matter did flow outward relative to the underdense center. More precisely, it moved toward the denser structures surrounding the region, while the low-density volume expanded faster than the cosmic average. But this was not a late cleanup operation. It was part of the same long process that assembled the walls, filaments, and clusters around it. This changes the meaning of the missing galaxies. A missing object can be absent for two very different reasons. It can be removed after it exists, or the conditions required to build it may never become strong enough. Boötes is mostly the second kind of absence. Large bright galaxies require dark matter halos, massive enough to capture gas, retain it, cool it, and sustain generations of star formation. If fewer such halos develop in an underdense environment, the final map contains fewer luminous systems. The deficit becomes visible in galaxies, even though the underlying region still contains dark matter and diffuse material. The void is not empty because matter vanished. It is sparse because structure formation proceeded unevenly. This conclusion is less cinematic than a cosmic explosion, but it reaches much deeper. An explosion would be one event. The hidden black hole would be one object. Primordial unevenness belongs to the initial architecture of the observable universe. The Boötes Void is therefore not a recent scar. It is an old difference amplified until it became enormous. Even the word old is inadequate. The stars inside the Milky Way are old. Many galaxies are old. The density pattern beneath Boötes began before any star existed, before atoms had gathered into the first luminous systems, while the future universe was encoded as tiny variations in matter and radiation. That history also explains why no clean wall appears today. A cavity blasted into material would have an event-defined boundary. A cosmological underdensity develops through gradients. Matter becomes gradually more abundant towards surrounding filaments and walls. The edge depends on the density threshold and tracer chosen by the observer. Nothing dramatic happens at one radius. The environment changes continuously. This is why ordinary physics remains enough. No law has to switch off. No region of space becomes forbidden to matter. The same gravity operates inside and outside the void. The expected motions would also betray any late evacuation. To clear a mature galactic population, enormous systems would have to acquire coordinated velocities away from the interior. Their stars, gas, and dark matter halos would move together. The boundary would preserve evidence of that violent migration in unusual speed patterns, disturbed structures, and an energy source capable of accelerating them. Instead, the motions around voids fit the gentler language of structure growth. Galaxies near the edges participate in flows toward denser walls, while the underdense region expands relative to the average. The velocities are cosmological consequences, not the debris pattern of one catastrophe. The age distribution offers another distinction. If a recent event had cleared the region, astronomers could expect a population that formed normally and was then displaced. A primordial underdensity predicts something else: fewer massive halos across cosmic history, altered opportunities for gas accretion, and a galaxy population shaped by long isolation rather than sudden removal. This is why later studies focus so strongly on the galaxies that remain. Their gas, stars, companions, and motions preserve the difference between a region that was emptied and a region that developed sparsely. The first story requires destruction. The second requires only unequal beginnings and enough time. And that leaves the strangest contradiction so far. Gravity attracts. It gathers gas into stars. It gathers stars into galaxies. It gathers galaxies into groups and clusters. Everything about gravity seems to favour concentration. How can an attractive force help an enormous region become emptier with time? The answer begins when the future Boötes Void was not yet visible at all. It was only a slight shortage. Return to the early universe. Long before galaxies, matter was distributed with extraordinary smoothness, but not perfect smoothness. Tiny density differences existed from place to place. Some regions contained slightly more matter than average. Others contained slightly less. The contrast was small enough that no human eye could have identified a future cluster or void. Yet gravity is patient. Given billions of years, a small advantage can become architecture. A region with slightly more matter exerts slightly more gravitational pull. It attracts material from its surroundings and becomes denser. As it gains matter, its pull strengthens further. The future cluster begins as a preference almost too small to describe, and ends as a knot containing thousands of galaxies. The underdense region follows the complementary path. Because it begins with slightly less matter, it attracts less strongly than the areas around it. Material near its edges responds more to neighbouring overdensities. Matter flows toward the forming walls and filaments. The underdense volume does not need to push anything away. It loses the competition for matter because other regions pull more effectively. Run the evolution forward in a simulation. At first, the particle field remains smooth enough to resemble mist. Faint concentrations then tighten. Threads emerge between them. The threads gain mass. Material streams toward their intersections, and bright knots begin to form where several streams meet. The future void is never switched on. It becomes visible only because everything around it grows faster. Frame by frame, the center declines in relative density, while the surrounding web sharpens. The darkness is not advancing like a substance. Contrast is accumulating around it. The volume also expands differently. The universe expands everywhere on large scales, but dense regions resist that expansion through gravity. A forming cluster can slow, collapse, and become gravitationally bound. An underdense region has less matter available to resist. It expands faster relative to the cosmic average. Imagine dots painted on a flexible sheet. Stretch one low-density part of the sheet slightly more than the surrounding areas. The dots there spread farther apart. Their individual masses do not need to shrink. The same amount of matter becomes diluted through a larger volume. For a cosmic void, that relative expansion deepens the underdensity. The density falls not because space is creating a repulsive vacuum in the center, but because matter is sparse and the region's volume grows. At the same time, material continues to gather more efficiently in the surrounding network. This produces a causal chain that can be followed without mystery. A slight primordial underdensity begins with less matter. Its gravity is weaker than that of neighboring overdensities. Matter flows preferentially toward those richer regions. The low-density volume expands faster relative to the average. Its matter becomes more diluted. Fewer dark matter halos reach the masses needed to host bright galaxies. The final optical map contains a major galaxy deficit. The galaxies did not need to be destroyed because many of their host halos never developed in the first place. Dark matter is essential to this story. It does not emit or absorb light in the way ordinary matter does, but its gravity supplies most of the framework on which cosmic structure grows. Regions containing more dark matter develop deeper gravitational wells. Ordinary gas falls into those wells, heats, cools, collapses, and forms stars. Inside a void, dark matter is not absent. Its density is lower. Small halos can still form. Some become homes for dwarf galaxies or larger gas-rich systems. But the population shifts. Massive halos become rare, and rich clusters become almost non-existent in the deep interior. This is why the visible galaxy deficit can appear more dramatic than the total matter deficit. Bright galaxies are biased tracers. They favour the densest peaks of the matter distribution. Remove many of those peaks, and an optical catalogue can look nearly empty, even though diffuse dark matter and gas continue through the volume. The universe is not divided into matter and no matter. It is divided into an extraordinary range of densities. The same process also explains why voids grow together with the structures around them. A cluster becomes more prominent as it gathers matter. A void becomes more prominent as it loses relative density. Neither can be understood alone, because each is defined against the same evolving average. Gravity builds the bright web by draining contrast from the spaces between its strands. That sentence can sound as though gravity literally sucks matter out of a finished cavity. The physical picture is slower. Particle trajectories respond to a changing gravitational field over cosmic time. Material near the underdense region drifts toward forming sheets and filaments. The interior expands. Halo formation is suppressed. The boundary becomes richer while the center remains poor. No single moment creates the void. It emerges. This is also why the process can generate enormous scales. The initial density fluctuations extended across many sizes. Some small underdensities were compressed or erased when they lay inside larger overdense regions. Others occupied broader low-density environments and merged into more extensive void complexes as surrounding walls developed. The future of an underdensity depends on its surroundings. A small void inside a larger void can expand and join neighboring basins. A small void embedded in a collapsing overdense region may be squeezed out of existence. Cosmologists call these broad evolutionary paths void in void and void in cloud behavior. For Boötes, the important possibility is that the famous region did not grow from one perfectly smooth spherical seed. Several low-density basins may have expanded within a wider underdense environment, separated by weak filaments and sparse galaxy groups. As the contrast grew, early surveys could interpret the connected scarcity as one vast void. The mechanism is ordinary. The result is not. A tiny initial shortage becomes a volume with a radius measured in hundreds of millions of light years. A difference too small to recognize in the early universe becomes one of the largest famous absences in the nearby galaxy distribution. The suppression of massive halos is not an all-or-nothing switch. Halo formation follows a distribution. In a dense region, more peaks cross the thresholds needed to become groups and clusters. Inside a void, the distribution shifts toward lower masses. Small halos remain possible, but the high-mass tail becomes thin. Gas then introduces further filters. A shallow halo may struggle to retain material heated by ultraviolet radiation from the young universe. Stellar explosions can push gas out of small systems more easily than out of massive ones. Cooling may proceed slowly. A dark matter halo can therefore exist without becoming a bright optical galaxy. These processes magnify the visual emptiness produced by the initial matter deficit. The dark matter underdensity reduces the number of potential homes. Baryonic physics determines which of those homes light up strongly enough to enter a survey. This layered picture explains why simulations must do more than follow gravity if they are to predict an observed galaxy catalogue precisely. They need a model connecting halos to stars, gas, and luminosity. Yet the broad void itself forms before those complicated details are added. Gravity creates the low-density framework. Galaxy physics decides how the framework appears in each wavelength. The Boötes Void is therefore both simple and difficult. Its origin follows a clean causal path. Its visible population depends on many local histories. And once the mechanism is understood, attention moves to the structures that make the void visible. The darkness needs edges. Imagine the Boötes region appearing on a galaxy map at 4 different moments in cosmic history. At first, there is no recognizable void. The matter field is almost smooth, with a shallow depression where the future underdensity will develop. Later, faint ridges begin to form around it. The ridges lengthen. Some intersect. Matter accumulates along them, and their intersections become brighter knots. The interior does not turn black, it simply fails to brighten at the same rate. By the present era, galaxies outline a network around the sparse volume. Sheets and filaments stretch along its sides. Groups gather where those structures meet. The underdensity becomes legible because the surrounding universe has become crowded enough to define it. The walls of a void are not physical walls. They are regions where the density rises relative to the interior. A spacecraft crossing one would not strike a barrier. It would enter an environment containing more halos, more galaxies, more gas, and stronger gravitational connections. The word wall comes from the map. When astronomers plot galaxy positions in slices, the distribution can resemble foam. Bright points gather along narrow boundaries. Large, low-density cells occupy the spaces between them. Filaments connect denser knots, and sheets extend across broader areas. This is the cosmic web. Boötes belongs to it completely. The void is not a defect between important structures. It is one of the structures. This requires a shift in how we imagine cosmic architecture. We naturally notice what shines. A galaxy appears to be an object. A cluster appears to be a larger object. A filament appears to be a chain of objects. A void is recognized by a probability. Choose a location inside it and ask how likely you are to find a bright galaxy within a given distance. The answer is much lower than in an average region. Move toward the boundary and that probability rises. Continue into a filament and it rises sharply. The transition is statistical, not material. This also means the walls do not need to surround the region as a sealed shell. Filaments can curve, branch, and leave openings. Sheets can be incomplete. Internal tendrils can cross part of the underdensity. One side may connect to a richer concentration than another. The familiar spherical image is therefore only a guide to scale. The real Boötes environment is shaped by neighbouring structures and by the way the survey samples them. At smaller scales, the interior can be divided again. A deep low-density basin may contain a thin filament. That filament may support several galaxies. On either side lie smaller subvoids. An algorithm designed to identify watershed basins might catalogue those as separate structures. Another algorithm might merge them because the internal ridge never reaches a chosen density threshold. Both maps can describe real features. They answer different questions. The hierarchy resembles a landscape viewed from different heights. From the ground, separate valleys appear distinct. From an aircraft, they may belong to one broad lowland divided by modest ridges. From orbit, the entire region becomes one depression within a continental pattern. Scale changes the label without changing the terrain. This matters for Boötes because the historical survey was sparse. A few sightlines established an extraordinary deficit, but they could not trace every weak internal structure. Later observations found galaxies and groups within the broad volume. Modern catalogues can describe a rougher geography than the original near-spherical picture. That does not invalidate the discovery. It improves the coastline. The large-scale environment remains underdense, even when smaller structures are added. A village does not turn a desert into a metropolis. A thin chain of galaxies does not erase the surrounding shortage. The hierarchy also affects galaxy evolution. A galaxy near the centre of a deep void experiences a different large-scale environment from one near a wall. A system inside a small internal filament may have close companions despite living within the larger Boötes underdensity. Local density and large-scale density can point in different directions. That distinction will become important later, because some galaxies found inside Boötes are not isolated in the simple sense. They may belong to pairs or small groups. Their nearest neighbours can influence them even while rich clusters remain absent across the wider region. The cosmic web does not switch off at the void boundary. It becomes faint. Dark matter screens can pass through the interior. Gas can follow them. Small halos can form along them. The network continues, but with less mass and fewer luminous markers. This gives the void a kind of internal anatomy. There is a centre, though different methods may place it differently. There are gradients toward richer surroundings. There are subvoids, weak ridges, sparse filaments, galaxy groups, and isolated halos. There are outflowing motions as matter responds to the surrounding density field, and there is a history encoded in all of it. A perfectly empty cavity would be simpler. It would contain no internal evidence. Boötes is scientifically valuable because it is not perfectly empty. The surviving structures reveal which parts of galaxy formation continue in extreme underdensity and which become suppressed. The walls explain how the void is outlined. They do not yet tell us everything that remains inside. A slice through the web also changes depending on orientation. Look along a filament and several galaxies may overlap in projection, making the structure seem compact. Look across the same filament and it becomes a long thread. A sheet viewed edge-on resembles a narrow wall. Face-on, it spreads into a broad, less obvious surface. Redshift maps help recover depth, but peculiar velocities blur the picture. The internal geography of Boötes is therefore not simply waiting to be photographed from the correct angle. It must be reconstructed by combining position, redshift, selection effects, and models of motion. This complexity gives the walls scientific value. Their galaxies respond to the mass deficit beside them. Their velocities reveal the outflow from the void. Their shapes and alignments can preserve aspects of the surrounding tidal field. The boundary is not merely where the point density rises. It is where the underdense interior connects dynamically to the rest of the web. The few objects inside can be equally revealing. A galaxy deep in the void samples one environment. A galaxy on an internal filament samples another. A system near the outer wall may have access to more gas and more companions. Treating all of them as one population would erase the very hierarchy the map has uncovered. The next survey, therefore, needed not just more points, but a different kind of point. For that, astronomers had to stop treating the darkness as a blank background and begin searching it with methods that did not depend only on bright, visible galaxies. The first answer is simple enough to be missed. Space remains. The Boötes Void contains the same expanding spacetime that connects every other region of the universe. Light passes through it. The cosmic microwave background fills it. Neutrinos cross it. Gravitational fields extend through it. There is no physical medium called emptiness occupying the interior. Matter remains as well. The average density is low, not zero. Dark matter forms the broad gravitational framework. Diffuse ordinary gas occupies the space between halos. Some gas may be warm or hot and extremely difficult to detect. Some remains cool enough to settle into smaller structures. Tiny halos can exist without forming many stars. Others host faint galaxies below the limits of early optical surveys. And bright galaxies remain, though they are rare. This is where language creates a trap. When astronomers say a region is almost empty of galaxies, the statement usually refers to a selected population, galaxies bright enough to enter a catalogue, of a type visible in a chosen wavelength range, within a measured redshift interval. Change the selection, and the map changes. A massive luminous galaxy is easy to see across large distances. A low surface brightness galaxy can spread the same light over a broad area and nearly disappear against the sky. A gas-rich dwarf may contain substantial neutral hydrogen, while forming too few stars to stand out optically. A dusty system may appear faint in visible light, but bright in infrared or radio emission. The early Boötes surveys were not wrong to use optical galaxies. Bright galaxies are excellent tracers of major structure. Their shortage established the void. But they were not the only possible tracers. Suppose a city were mapped only by buildings taller than 50 floors. The business centre would blaze with markers. Residential districts would become sparse. Small towns could vanish completely. The map would still reveal where the greatest concentrations lie, but its blank regions would not be uninhabited. Bright galaxy maps work in a similar way. They emphasize the highest peaks of the cosmic density field. Voids appear especially dramatic because the halos capable of hosting those peaks are rare there. Fainter systems sample lower peaks and reveal more texture. Astronomers therefore began searching for galaxies inside Boötes, rather than merely measuring how many were missing. Each detection asked a more useful question. What kind of galaxy can form in such an environment? Does it retain more gas because encounters are rare? Does it form stars slowly because the supply of fresh material is limited? Is it genuinely isolated? Or does it belong to a small local group hidden inside the wider underdensity? Do void galaxies differ because of the void itself, or because they tend to occupy lower mass halos? The interior population could turn the absence into a laboratory. Optical observations found galaxies within the broad Boötes region, proving early that the void was not sterile. Yet optical light alone could miss exactly the systems most likely to survive there: faint, gas-rich galaxies with modest star formation. Neutral hydrogen offered another way to listen. Hydrogen is the most abundant ordinary element in the universe. In cold interstellar space, neutral hydrogen atoms can change the relative alignment of the proton and electron spins. The transition releases a photon with a wavelength of about 21 centimeters. The event is extraordinarily weak for one atom. A galaxy contains so many hydrogen atoms that the combined signal becomes detectable by radio telescopes. The 21 centimeter line carries two kinds of information at once. Its frequency shift gives the velocity of the gas, allowing astronomers to estimate distance in the same broad redshift sense used for optical galaxies. Its brightness reveals how much neutral hydrogen is present. A radio survey can therefore find a galaxy through its fuel, even when its starlight is unimpressive. The method has limits. Distance weakens the signal. Radio interference can contaminate observations. Telescope beams cover broad regions of sky, sometimes blending nearby systems. The conversion from signal to hydrogen mass requires calibration and an assumed distance. But the line reaches into a different population. This mattered enormously for Boötes. If the void contained only a few old, gas-poor galaxies, its interior might represent an environment where galaxy growth had largely failed. If it contained previously uncatalogued reservoirs of neutral hydrogen, then the darkness could hide active, evolving systems overlooked by optical selection. The radio search was not expected to make the void crowded. Its purpose was to discover what kind of structure survived beneath the bright galaxy threshold. The distinction between local and large-scale environment became central. A galaxy can sit within a vast underdensity while still having a companion 100,000 light-years away. Those two systems may exchange gas, distort one another, or eventually merge. On a 1 megaparsec scale, the neighborhood may feel populated. On a 100 megaparsec scale, it remains profoundly sparse. This is not an exception to void structure. It is what hierarchical structure predicts. Small concentrations can exist inside large depressions. A hill can stand on the floor of a valley without becoming a mountain range. A compact galaxy group can inhabit Boötes without turning the void into an average region. Neutral hydrogen is especially useful because its signal can reveal motion without requiring the galaxy to be visually impressive. A spectrum spread across several radio channels may show a double-horned profile, the combined signature of gas rotating on the approaching and receding sides of a disk. The width of the profile provides information about rotation, while the integrated signal estimates the total HI mass. For a resolved source, the data become richer. Every position on the sky contains a small spectrum. Stack those spectra into a cube, and astronomers can move through velocity one channel at a time. Gas appears, shifts across the source, and fades. Companions that overlap in an optical image may separate cleanly in velocity. A faint cloud with little starlight can announce itself as a coherent radio feature. This is why the word listen is more than a metaphor. Radio astronomy converts an invisible atomic transition into a map of material and movement. The telescope is not hearing sound, but it is detecting a wavelength whose information is hidden from the eye. The method also exposes absence honestly. An HI non-detection does not prove that no galaxy exists, because a system may be gas poor or below the sensitivity limit. A detection, however, can establish that cold atomic fuel occupies a location the optical catalogue overlooked. The next observations would expose that hierarchy directly. Astronomers pointed one of radio astronomy's most recognizable instruments towards selected Boötes galaxies and began building data cubes in which 2 dimensions represented the sky, while the third represented velocity. The void was about to acquire another layer, and when the radio signal arrived, the silence did not disappear. It broke into neighborhoods. The Very Large Array in New Mexico is arranged not as one dish, but as many antennas working together. Seen from the air, its rails form a giant Y across the desert. The antennas can be moved into different configurations, changing the balance between sensitivity to broad diffuse emission and the ability to distinguish smaller structures. For the Boötes survey, the array observed 24 fields and produced radio data cubes covering roughly 1100 cubic megaparsecs, about 1% of the enormous historical void volume. That fraction is important. The survey did not scan the entire void blindly. It examined selected regions around known galaxies. Its discoveries, therefore, revealed local structure near those targets, not a complete census of everything inside Boötes. Within the observed volume, the radio maps detected neutral hydrogen associated with 16 targeted galaxies. Then additional signals appeared. 18 H1 sources were found that had not been listed as galaxies in the optical catalogues used to select the fields. The blank map gained objects through a wavelength the earlier census had not used. Some radio detections corresponded to faint optical galaxies that became recognizable once astronomers knew where to look. Others revealed systems whose visible light had not been catalogued at all. The neutral hydrogen acted like a marker floating above structures almost lost against the optical sky. The result did not fill the Boötes void. 1100 cubic megaparsecs is an enormous survey volume by ordinary standards. But within the historical void, it was only a sample. 34 detections across those fields did not create a hidden metropolis. What changed was the texture. Several objects appeared in pairs. Others belonged to loose groups. The survey identified systems that might form a compact group, with galaxies close enough for mutual gravity to matter. This was the midpoint reversal. The interior was not a smooth population of solitary islands distributed at random, at least around the selected targets. Galaxies showed small-scale clustering. When the researchers counted neighbours within distances of roughly 1 megaparsec, the local density around the Boötes targets was not orders of magnitude below comparable environments. Depending on the exact comparison and scale, it remained within about a factor of 2 of control samples. The large-scale environment was extremely poor. The local environment could still be ordinary enough to support interactions. Picture a continent with almost no cities. Travel across it by air, and the lights remain scarce for hundreds of kilometers. Land near one settlement, however, and you may find several houses, roads, farms, and a neighboring village. The continent remains underpopulated. The village still has neighbors. That is the structure the radio data revealed. The detections were also biased toward lake-type, gas-rich systems. Spiral and irregular galaxies often retain more neutral hydrogen than elliptical galaxies. Their disks can support ongoing star formation. Inside an underdense environment, where high-speed cluster encounters and hot intracluster gas are absent, such systems may preserve cold gas differently from galaxies in dense regions. Again, interpretation requires care. The survey targeted known galaxies, so it was designed to find gas near places where optical objects were already present. It did not prove that every part of the void contained similar groups. It also could not show that all differences resulted from the void rather than from galaxy mass, morphology, or selection. What it proved was narrower and more valuable. The Boötes interior contains more small-scale structure than a bright optical map alone suggests. Neutral hydrogen survives there. Faint galaxies survive there. Pairs and groups survive there. Galaxy interactions are possible there. A huge underdensity does not erase local gravity. The data cubes made this visible through motion. Neutral hydrogen in a rotating galaxy does not emit at one exact frequency across the whole disk. Gas on the approaching side is shifted slightly one way. Gas on the receding side is shifted the other. Move through the velocity channels and the emission appears across different parts of the galaxy. The radio observer does not merely see a spot. The observer sees a system moving. In interacting pairs, the gas distribution can stretch, overlap, or become asymmetric. In loose groups, several signals appear at related positions and velocities. These patterns reveal relationships that a single optical image may not make obvious. Boötes, therefore, changed from a negative discovery into a positive one. The original question had been, why are so many galaxies missing? The radio question became, what are the remaining galaxies doing? They were rotating. They were carrying large reservoirs of atomic gas. Some were living close enough to companions for local evolution to continue through encounters. The void had neighborhoods. That line should not be mistaken for a claim that the region is secretly crowded. The contrast between scales remains the point. Around an individual target, a companion may lie within a few 100,000 or a million light years. Beyond that local pocket, the distribution thins. Rich groups and massive clusters become scarce. The broader density field remains low across tens of millions of light years. Local normality is embedded inside large-scale abnormality. This is one of the most useful corrections the Boötes observations provide. Human intuition often wants one label to apply at every scale. A place is empty or inhabited, isolated or connected, normal or extreme. The universe does not organize itself so cleanly. A galaxy can be isolated from the cosmic web's major structures and still share gas and gravity with a close companion. A radio field can contain several detections, while the surrounding 100 megaparsec volume remains one of the most famous underdensities known. The wavelength determines which truth becomes visible. Optical light reveals accumulated starlight. 21 centimeter radio emission reveals neutral hydrogen. Neither map is the entire reality. Combined, they describe a population of gas-bearing systems living within a much larger shortage of massive luminous structure. The control comparison was crucial. Finding several neighbours around selected targets might sound surprising, only because the word void primes us to expect complete isolation. By comparing similar galaxies outside the deepest underdensity, researchers could ask whether the local clustering was truly exceptional. The answer was nuanced. On the small scales sampled, the difference was modest compared with the enormous contrast on larger scales. That result changes the causal story of galaxy evolution. A void galaxy is not automatically untouched. A close companion can still pull gas into a tidal bridge, compress clouds, or disturb a disk. What disappears first in a void is not every interaction. It is the dense hierarchy of groups, clusters, and repeated encounters common to richer regions. The radio survey also demonstrated why one average density cannot describe an environment. The same target can have a relatively ordinary neighbour count within 1 megaparsec and an extraordinary deficit within tens of megaparsecs. Both measurements are correct. They describe different radii around the same galaxy. For later studies, this becomes a warning. If void galaxies show unusual star formation, researchers must separate large-scale underdensity from the influence of immediate companions. Otherwise, a local merger may be attributed incorrectly to the void, or a large-scale environmental effect may be hidden by one nearby system. The radio detections did more than add galaxies. They changed what questions could be asked about cause. That discovery created a new question. Were these galaxies merely ordinary systems placed in an unusual address, or had the void changed the way they evolved? A survey of several dozen objects can reveal a population. To examine internal evolution, astronomers needed to move closer to one system, map its cold molecular gas, and watch how that gas rotated. One galaxy would not represent the whole void, but it could show what a normal-looking disk becomes when the larger universe around it is anything but normal. That galaxy is known as CG 910. From a distance, CG 910 does not resemble a cosmic impossibility. It is a disk galaxy containing stars, dust, dark matter, atomic hydrogen, and molecular gas, the same broad ingredients found in galaxies throughout the nearby universe. Nothing in its structure suggests that physical law weakens inside Boötes. Gravity gathers matter. Gas settles into orbit. Stars continue to form. Yet CG 910 developed within an extremely underdense, large-scale environment, where the usual network of rich groups and crowded filaments becomes thin. That makes the system useful for a reason almost opposite to spectacle. It offers a quieter experiment. In dense environments, the galaxy's history can become entangled with everything around it. A close companion pulls at the disk. A merger drives gas toward the centre. A cluster's hot atmosphere can strip cold material away. Repeated encounters disturb stellar orbits and reshape spiral structure. Look at a galaxy after billions of years of that traffic, and it can be difficult to separate internal evolution from environmental damage. Inside a void, much of the large-scale traffic is reduced. A galaxy may spend longer changing through its own bars, spiral waves, feedback, gas cooling, and gradual star formation. Astronomers refer to this broad category as secular evolution, change driven mainly by internal processes rather than major external disruption. Researchers used a combined array for research in millimeter wave astronomy, known as CARMA, to observe carbon monoxide emission from CG 910. Molecular hydrogen is the principal raw material from which stars form, but cold molecular hydrogen is difficult to observe directly under common galactic conditions. Carbon monoxide emits more accessible spectral lines and is used as a tracer. From the distribution and brightness of that emission, astronomers can estimate where molecular gas lies and how much is present. The observations revealed a molecular disk roughly 7 kiloparsecs across. That is more than 20,000 light-years, large enough to span a significant part of the galaxy's stellar body. The estimated molecular gas mass was about 12 billion times the mass of the Sun. Inside one of the emptiest famous environments in the nearby universe, the galaxy had retained a major reservoir of dense star-forming fuel. The motion of the gas was equally revealing. Across the carbon monoxide map, one side of the disk moved toward us while the other moved away. The ordered pattern flattened at a rotation speed of roughly 256 kilometers per second. There was no clear sign in the mapped molecular disk of a recent major interaction or a large stream of gas crashing inward. No violently twisted velocity field dominated the observation. The disk rotated with the settled behaviour of a mature gravitational system. This does not prove that CG 910 has never interacted. A galaxy can relax after older disturbances, and a molecular map cannot preserve every event in its past. The result supports a quieter interpretation rather than establishing eternal isolation. Still, the contrast is striking. The void did not prevent the galaxy from becoming organized and massive. It may have allowed the disk to spend longer without the kinds of major interruptions common in richer environments. Now imagine standing on a planet inside CG 910. You would not look into a blank sky containing one lonely star. You would be inside a galaxy. Stars would surround you. The galactic plane might cross the darkness as a dense band. Dust clouds could hide distant suns. Stellar nurseries might glow within clouds of ionized gas. Locally, the universe could feel full. The void would reveal itself only when astronomers on that world measured galaxies beyond their own disk. Nearby rich clusters would be missing. Massive neighbours would be rare. The wider map would thin sooner and remain sparse longer than the maps made from denser cosmic environments. Inside the galaxy, the universe can feel normal. The abnormality begins outside it. The Green Bank telescope added another part of the gas inventory by measuring neutral atomic hydrogen. Atomic gas is generally more diffuse than molecular gas and often extends beyond the active star-forming disk. It can serve as a reservoir from which future molecular clouds develop. CG 910 contained an estimated atomic hydrogen mass of roughly 3 billion solar masses. That is enormous in human terms, yet relatively modest compared with its molecular gas and stellar content. The galaxy's stellar mass was a little above 20 billion solar masses, while a substantial portion of its remaining cold gas was already in the molecular phase. The fuel was present. Its conversion into new stars appeared comparatively slow. Astronomers describe this using a depletion time, the available molecular gas divided by the current star formation rate. It is not a prophecy of exactly when the gas will disappear. New material may arrive, feedback may expel gas, and the rate can change. It is a way of comparing how quickly different galaxies are using their present reservoirs. For CG 910, the inferred depletion time was long. The system appeared to be evolving slowly, consistent with a picture in which internal processes dominate more often than violent external events. One galaxy cannot prove that the void caused this behavior. Halo mass matters. Internal dynamics matter. Magnetic fields. Stellar feedback. Past accretion. And old encounters matter. CG 910 is a case study, not a summary of every system in Boötes. But it demonstrates something the first empty-looking graph could never show. Void evolution is not failed evolution. Galaxies there can build stellar disks, organize cold gas, rotate rapidly, and continue forming stars. They may simply do so along a different schedule. In a cluster, evolution can arrive as violence. Inside Boötes, it may arrive as delay. Fewer major encounters, longer intervals of internal rearrangement, a large reservoir consumed on a slower clock. The conversion from carbon monoxide brightness to molecular hydrogen mass also carries uncertainty. The relationship depends on metallicity, temperature, density, and the physical state of the gas. Researchers therefore treat the quoted molecular mass as an estimate tied to an adopted conversion factor, not as a perfectly counted inventory of molecules. That uncertainty does not erase the main result. The CO emission is extended, organized, and dynamically consistent with a substantial rotating molecular disk. Whether the exact mass shifts within reasonable limits, CG 910 is not a tiny remnant barely holding fuel. It is a developed galaxy with a serious cold gas component. The long depletion time is equally easy to misunderstand. It does not mean the galaxy will continue unchanged until a clock reaches zero. Star formation can accelerate, feedback can heat or remove gas, and new material may arrive. The measurement simply compares the present reservoir with the present rate of consumption. In that snapshot, CG 910 uses its molecular gas slowly. This is the scientific value of the case, not proof of one universal void lifestyle, but a detailed example consistent with long secular development in an environment where major external disturbances are less frequent. The system makes the void personal, without making it anthropomorphic. Its gas responds only to physics, yet its quiet order gives the surrounding isolation a visible center. CG 910 turns inside the underdensity without announcing where it lives. Zoom beyond the molecular disk, and it becomes one island. Move farther, and the nearby population thins. Continue outward, and the scale of Boötes dominates again. The ordered galaxy contracts to one point. Then even that point nearly disappears. Its existence leaves the story with a larger question. If an ordinary rotating disk can form and survive there, and if gravity explains the broad architecture, perhaps the Boötes Void is not an impossible object at all. Perhaps it lies at the extreme end of something modern cosmology already knows how to make. When the original surveys were published, that question carried real pressure. In 1981, the uncomfortable part was not merely that the graph contained a gap. The gap appeared broad, coherent, and difficult to reproduce, with several structure formation models being discussed at the time. The known maps were small. The simulated universes were smaller. Astronomers had not yet measured enough cosmic volume to know how far into the rare tail a natural underdensity could extend. Boötes arrived before the comparison population did. That historical discomfort was not a mistake. Science should become uncomfortable when observation exceeds expectation. The error would be preserving the original discomfort after the expectations and evidence have changed. A cosmological model is not tested by asking whether it can draw one exact copy of Boötes at one exact position. It is tested statistically. Begin with early density fluctuations consistent with observation. Evolve them under the model's laws. Create a volume large enough to contain rare structures. Then ask whether the resulting population includes voids with comparable scales, depths, profiles, and abundances. This demands two things that early computers struggled to provide at the same time. The simulated box must be enormous. If it is too small, the rarest voids cannot appear because there is not enough volume for the statistical tail. The simulation must also resolve enough structure to identify halos and galaxies. A coarse calculation may represent broad density waves, while losing the smaller systems that determine how an observed galaxy catalogue would look. Volume and detail compete for computing power. For years, that competition limited the comparison. Then the virtual universes grew. Modern lambda CDM simulations begin with a nearly smooth density field, containing the small fluctuations measured from the early universe. Cold dark matter supplies most of the gravitational framework. The Greek letter lambda represents the component associated with accelerated cosmic expansion. Gravity amplifies the density differences, while expansion changes the rate at which structure grows. Run the calculation forward, and the familiar architecture appears. Dense knots collapse. Filaments connect them. Sheets develop around broad, low-density regions. Voids expand relative to the average. The important result is not that programmers place empty spheres into the box. The voids emerge from the same initial conditions in gravitational evolution that produce clusters. Once the simulated volumes became large enough, the rare tail appeared. One major analysis in the mid-2000s applied a defined density threshold to large lambda CDM simulations and identified nearly 80,000 voids above its chosen minimum scale. In the largest simulated volume, the biggest void reached an effective radius approaching the historical scale associated with Boötes. That did not make every detail identical. It changed what could honestly be claimed. Large voids were no longer absent from the model. They were embedded within its natural population. Boötes had not become ordinary. It had become possible. Cosmic variance is the name given to part of this problem. We observe one universe from one location, and any finite survey samples only part of its possible structure. A region containing an unusually large void may be statistically legitimate, even if a smaller survey would almost never include one. Simulations address this by creating many independent volumes, or by analysing very large boxes containing numerous sub-regions. Researchers can then estimate not only the average void population, but the spread expected from one cosmic volume to another. The rarest objects are sensitive to this spread. If a model predicts one Boötes scale structure per enormous volume, a survey slightly smaller than that volume may contain none, while another contains one. The absence or presence of a single example is therefore a weak statistical test. This is also why the phrase "most disturbing anomaly" must not be translated into a formal statement that Boötes is the least probable object in the universe. Its fame comes from history, scale, and the clarity of the original deficit, not from a completed ranking against every known void under one definition. The model question is narrower. Does the probability become so low that the observation remains implausible after survey size, selection, and definition are included? Modern work has not established that level of conflict. This distinction is essential because rare is not the same as forbidden. Imagine measuring human height in one small village and discovering someone far taller than every person in the sample. The individual may initially appear beyond expectation. Expand the sample to millions of people, and the same height may occupy an extreme but legitimate tail. The person remains unusually tall. The larger dataset changes whether the height requires a new biology. Boötes followed a similar path. The early surveys revealed a structure beyond the familiar sample. Wider catalogues and larger simulations supplied the population needed to interpret it. Modern redshift surveys now identify vast numbers of voids. Depending on the catalogue and algorithm, underdense regions occupy a majority of the surveyed cosmic volume, while containing only a small fraction of its bright galaxies. That statement shifts the emotional centre of the story. Boötes is not disturbing because it is the only emptiness of its kind. It is disturbing because emptiness is a normal part of large-scale architecture. Most luminous matter gathers into a relatively small portion of cosmic volume. The spaces between the bright structures are not leftover gaps in an otherwise filled universe. They are a major component of the web. Still, one should not leap from simulations make large voids to Boötes is completely solved. A simulated dark matter void and an observed bright galaxy void are not automatically equivalent. The simulation may define underdensity using particles. The survey may define it using luminous galaxies. One catalogue may search for spheres below a threshold. Another may divide the density field into irregular basins. The initial conditions, cosmological parameters, galaxy formation model, resolution, and survey selection all influence the comparison. The strongest conclusion is therefore measured rather than triumphant. Lambda CDM naturally creates a cosmic web containing very large underdensities. Some simulated voids reach scales comparable to historical estimates for Boötes. Large observational catalogues broadly resemble mock catalogues generated from the model. The mere existence of Boötes does not presently require a rupture in known cosmology. That sentence closes the original model crisis, but it opens better tests. Do simulations produce the correct number of the most extreme voids? Do the density profiles match? Do galaxies move around the boundaries at the expected speeds? Does weak gravitational lensing reveal the predicted total matter deficit? Do small halos and faint galaxies form in the expected numbers inside the deepest interiors? One celebrated void cannot settle those questions. A population can. Before that population can be compared fairly, however, every catalogue must answer a problem the universe does not solve for us. Where does one void end? Put the same three-dimensional galaxy map on 3 screens. On the first screen, an algorithm searches for the largest sphere whose average galaxy density falls below a chosen threshold. It expands the sphere until too many tracers enter. The result is one center and one radius. On the second screen, a watershed algorithm treats the density field like a landscape. It finds local minima and follows the rising density around them. The broad Boötes region separates into several connected basins, divided by weak ridges. On the third screen, the galaxy catalogue goes deeper. Fainter systems appear inside areas that looked empty before. Some basins shrink. Some internal ridges become clearer. A few regions no longer satisfy the original threshold. The galaxies have not moved. The question has changed. Boötes can be physically real and numerically unstable at the same time. There is no luminous shell around it. Density changes gradually. Any boundary is an operational decision, a rule designed to identify a meaningful feature within a continuous field. The first decision concerns the tracer. Bright galaxies strongly favour dense environments. They mark clusters and filaments clearly, but they can exaggerate the visual emptiness and voids. Add faint galaxies and low-mass systems, and the interior gains points. Map dark matter in a simulation, and the region gains even more small-scale structure. The large deficit persists. Its measured depth changes. This is tracer bias. The objects used to reveal matter do not sample every environment in the same proportion. A map made only from skyscrapers would identify urban centres beautifully, while making villages disappear. The blank portions would still be less urban, but their apparent emptiness would depend on what counted as a marker. A bright galaxy map does something similar to the universe. The second decision concerns shape. A spherical finder produces a convenient radius. It can be applied consistently and compared across catalogues. But real voids are not required to be spheres. They can be elongated, flattened, branching, or connected through low-density corridors. A watershed finder preserves more of that irregular geometry. It may also merge many subvoids into one enormous complex if the ridges between them remain weak. Change the merging rule and the object's size changes. This is one reason record claims are difficult. The largest void may mean the widest single diameter, the greatest connected volume, the largest equivalent sphere, the deepest central deficit, or the most extensive complex created by merging neighbouring basins. Those are different records. Astronomers often report an effective radius for an irregular void. They calculate the radius of a sphere containing the same volume. The number makes comparisons easier without claiming that the actual boundary is round. A crumpled object and a smooth ball can have the same volume. Their effective radii match. Their geometry does not. The number is therefore a compression of shape. Useful for population statistics, but insufficient for reconstructing the paths of filaments, the position of the deepest minimum, or the distance from a particular galaxy to the nearest wall. Those details require the full catalogue rather than one radius. Survey boundaries create another danger. A void finder may see an empty region near the edge of the observed sky because the catalogue simply stops there. Masks placed around bright foreground stars, dusty portions of the Milky Way, or incomplete observations can produce artificial gaps. Reliable catalogues therefore reject or flag voids touching uncertain boundaries. Missing observation must not be confused with missing matter. Redshift space introduces still another distortion. The measured redshift of a galaxy includes cosmic expansion and the galaxy's own motion through its local gravitational field. Around a void, matter tends to move outward relative to the underdense centre and toward the surrounding walls. These velocities can stretch or compress the reconstructed shape along our line of sight. A structure that appears elongated in the map may be less elongated in real space. Correcting the effect requires a model of the velocity field, and the velocity field is itself one of the quantities cosmologists hope to test. Even the distance unit may contain an assumption. Sizes expressed with a factor related to the Hubble constant cannot be turned into one ordinary number until an expansion rate is chosen. None of this means the Boötes Void is an artifact. It means a void is not a stone that can be lifted from the ground and measured with a ruler. Its existence is physical. Its catalogue identity is constructed from explicit rules. The fair comparison with simulation must use the same rules on both sides. If observed voids are found using bright galaxies, researchers create mock galaxy catalogues from the simulation and run the same finder. They reproduce survey masks, selection limits, redshift distortions, and measurement uncertainties as closely as possible. Otherwise, a difference between catalogues can masquerade as a failure of cosmology. Merging rules can create a phenomenon similar to coastlines joining when sea level changes. Raise the density threshold and shallow ridges disappear beneath the chosen boundary, connecting neighbouring basins into one vast complex. Lower the threshold and those ridges re-emerge, dividing the complex into smaller voids. Neither choice is automatically wrong. One may be useful for studying the deepest interiors, another for tracing connected low-density environments. The danger begins when measurements from one definition are compared with predictions from another as though the objects were identical. The centre can move as well. A spherical finder may choose the location farthest from bright galaxies. A watershed catalogue may use a volume-weighted barycenter. The deepest density minimum may lie somewhere else. When researchers stack voids to measure lensing or galaxy motion, the definition of the center affects how sharp the average signal becomes. Boötes illustrates the problem vividly because its popular image is so clean. One circle, one diameter, one empty interior. The scientific object is messier, a broad underdensity with internal galaxies, possible subvoids, and boundaries that depend on the census. Messiness is not weakness. It is information about the real density field. The aim is not to force the universe into a perfect sphere, but to use definitions that preserve the property being tested. This methodological discipline changes how the word anomaly should be used. A structure may be unusual within one catalogue and less unusual within another. Merging neighbouring basins can move it deeper into the statistical tail. Dividing the same complex can produce several less extreme objects. Detecting fainter galaxies raises the measured interior density. A different distance conversion changes the physical scale. Before anyone declares Boötes impossible, the impossibility must survive the tracer, the boundary rule, the algorithm, the survey mask, the redshift correction, and the cosmological ruler. That is a much higher standard than one spectacular diameter, and it leads to the cleanest scientific question in the entire story. What observation would genuinely make Boötes a serious problem for modern cosmology? Not one surprising map, not one large radius, not one galaxy behaving differently from an average system. A true conflict would need to survive several tests. The first is abundance. Suppose astronomers construct a large, carefully defined void catalogue from a well-understood survey. They create matched, mock catalogues from many lambda CDM simulations and apply the same finder to both. If structures as large and deep as Boötes appear far more frequently in the observed universe than in the simulations, the discrepancy could become significant. One rare void is weak evidence because rare objects must exist somewhere in a large enough volume. An excess population is stronger. The second test is the matter profile. Bright galaxies can exaggerate underdensity. A deep optical gap might arise partly because massive luminous systems avoid the region more strongly than the underlying dark matter does. Measuring the total deficit requires signals that respond to mass rather than starlight alone. Weak lensing offers one route. Shapes of many background galaxies are averaged around many foreground voids. Any one image is dominated by the galaxy's intrinsic form and observational noise, but a coherent statistical distortion can reveal the missing surface mass density. The signal must be stacked carefully, because an incorrect center or a mixture of very different void types can blur it. Galaxy velocities provide another route. If the matter deficit is deep, the surrounding gravitational field produces a characteristic outflow pattern. The observed redshift space distortion depends on viewing angle and distance from the center. Comparing that pattern with matched simulations tests both the density profile and the growth rate of structure. The cosmic microwave background may also be examined behind large underdensities for subtle temperature shifts produced as photons cross evolving gravitational potentials. Such measurements are difficult and population dependent, but they offer an independent connection between voids and the changing large-scale gravitational field. A serious conflict would require these mass-sensitive probes to point in the same direction, a region broader, deeper, or dynamically more extreme than the galaxy catalogue alone suggests, with no reasonable model able to reproduce the combination. To challenge the model, astronomers would need evidence that the total matter distribution also departs from prediction. Weak gravitational lensing can help measure the average mass deficit. Galaxy velocities around the boundary reveal how matter responds to the gravitational field. Other reconstruction methods estimate the underlying density from the surrounding large-scale structure. If the observed profile remained too deep, too broad, or dynamically inconsistent after those measurements, the problem would move beyond galaxy selection. The third test is the internal population. CG910 is informative, but one system cannot establish a cosmological failure. researchers would need a systematic mismatch across many void galaxies, too many or too few low-mass halos, unexpected gas fractions, star formation histories that simulations cannot reproduce, or dwarf galaxy populations inconsistent with the predicted dark matter framework. The mismatch would also have to survive differences in galaxy mass and local environment. A small galaxy near a void wall should not be compared casually with a massive system near the centre. Researchers would also need to reproduce the selection of those galaxies in synthetic surveys. Otherwise, a missing population of faint dwarfs might reflect telescope sensitivity, surface brightness limits, or an incomplete model of how stars occupy low-mass halos, rather than a failure in the underlying matter distribution. Statistical significance must also account for the number of opportunities to find something extreme. Search enough sizes, redshift ranges, sky regions, and void definitions, and one result may appear improbable by chance. Researchers call this broad issue the look elsewhere effect. A claim becomes stronger when the test is specified in advance or reproduced in independent data. Systematic errors can imitate tension as well. A calibration drift may alter galaxy selection with distance. Incomplete spectroscopy may create artificial gaps. Stellar contamination, dust extinction, or fiber placement limits can change the apparent density in ways that correlate across the sky. Matched mock surveys are designed to pass simulations through the same imperfections. The simulated universe is observed as though it were real. Galaxies are selected by brightness. Masks are applied. Redshift errors are added, and the same catalogue pipeline is run. Only then does a difference begin to isolate cosmology, rather than survey machinery. A convincing failure would therefore be difficult to produce, and that is exactly why it would matter. It would not be one spectacular object placed beside a generic simulation image. It would be a discrepancy that survives every ordinary explanation researchers can test. Boötes remains valuable because it helped define this standard. Its discovery forced astronomers to ask what the models truly predicted and what the observations had truly measured. The fourth test is methodological survival. Independent teams using genuinely independent surveys should recover the same tension, rather than inheriting one catalogue's assumptions. The discrepancy must remain when several reasonable void finders are used. It must survive deeper tracer samples, survey masks, redshift space corrections, and changes in the galaxy halo model. Independent surveys should recover the effect. This is the standard the strongest use of the word anomaly has to survive. Boötes has not crossed that threshold. It remains an extreme observed environment and a historically disruptive discovery. It is not currently a confirmed failure of the standard cosmological framework. That conclusion does not close the case forever. Cosmological models are successful approximations tested against expanding evidence. Dark energy remains poorly understood at a fundamental level. The properties of dark matter remain incomplete. Neutrino masses influence the growth of structure. Modified theories of gravity can alter void profiles and galaxy motions. Baryonic processes complicate how luminous galaxies occupy dark matter halos. Voids can test all of these effects precisely because they occupy the low-density end of the universe. But uncertainty does not make every explanation equal. There is no measured evidence that an advanced civilization removed the galaxies. No central mass has been found that could consume them. No observation identifies a portal, a simulation boundary, or a scar from another universe. Those ideas make no unique successful prediction for the Boötes data. And ordinary gravitational structure formation already explains the broad phenomenon. The remaining mystery is narrower and stronger. How accurately does the standard model reproduce the most extreme low-density environments when the measurement is made fairly? That question can be answered. It requires larger catalogues, deeper galaxy samples, better lensing measurements, improved simulations, and statistics drawn from thousands of voids rather than one famous name. The Boötes Void began as an apparent exception. Its future scientific value lies in becoming part of a population. Boötes alone cannot measure dark energy. Its contribution is more foundational. It taught astronomers how much information can be hidden inside a deficit. Once thousands of voids are mapped by the same rules, The absence becomes statistical, and statistics can test the universe. A cluster is loud with gravity. Thousands of galaxies move through an enormous concentration of dark matter. Hot gas fills the space between them. Mergers, high-speed encounters, and local gravitational effects overlap. A void is quieter. Its density is low. The local gravitational landscape is simpler in several respects. Matter remains present, and the surrounding web still influences the interior, but the extreme concentrations found in clusters are absent. That quiet makes subtle effects measurable. Begin with geometry. On the largest scales, the universe has no preferred direction. A population of voids may contain individual structures that are stretched, flattened, or irregular, but after enough are aligned and stacked, the average should not point one way more than another. Astronomers observe angles across the sky and redshifts along the line of sight. To convert those measurements into physical distances, they must assume a cosmological expansion history. If that assumed history is wrong, the conversion across the sky and the conversion along the line of sight become inconsistent. The stacked voids appear systematically stretched or compressed. The voids have not changed. The ruler is wrong. This is the Alcock-Pajinsky test, expressed through some of the largest natural shapes available. Something whose average geometry should be directionless becomes a test of the model used to reconstruct it. Galaxy motions add another signal. Matter near a void responds to the surrounding density field. Galaxies tend to move outward relative to the underdense center and toward walls and filaments. Their peculiar velocities alter the redshifts used to map them. Earlier, this created a complication. Now it becomes data. The pattern of stretching and compression around a large void depends on how structure grows. That growth depends on the amount of matter, the behavior of cosmic acceleration, and the law of gravity. General relativity predicts one statistical relationship between density and motion. Modified theories can predict another. A large sample of voids allows astronomers to compare those patterns in the weakest gravitational environments of the cosmic web. There is also a way to weigh the deficit directly. Matter bends light. A galaxy cluster contains more mass than average and can magnify or distort background galaxies. A cosmic void contains less mass than average. Light passing through its region experiences a slightly different gravitational landscape. The lensing signal from one void is tiny. Stack many voids, and the average distortion can reveal the underlying matter deficit, including dark matter that emits no light. Galaxy counts show where the luminous traces are missing. Weak lensing tests whether the mass is missing to the expected degree. This distinction reaches back to the first Boötes graph. The original discovery used galaxies as markers. Future population studies can combine those markers with gravity itself. Void abundance adds another constraint. How many underdensities exist at a given radius and depth? How does the distribution change with cosmic time? A model that changes the growth of structure can alter the number of small voids, the merging of neighboring basins, and the profiles of the largest regions. Massive neutrinos can suppress structure on particular scales. Alternative dark energy histories can change how quickly contrast grows. Modified gravity may affect low-density regions differently from dense, screened environments. The void population remembers these influences. No one measurement is decisive. Geometry, galaxy motion, weak lensing, density profiles, and abundance carry different uncertainties. Their power comes from combination. Stacking does not mean pretending every void is identical. Researchers sort them by size, depth, redshift, or environment before combining the signal. A small void embedded in a dense region may evolve differently from a large expanding basin. Mixing the categories can wash out the very physics being sought. Cross-correlation provides another tool. Instead of examining only the galaxies assigned to a void, astronomers measure how galaxy density changes with distance from many void centers. The average profile reveals a depleted interior, a rising boundary, and sometimes a compensating ridge where matter has accumulated. That profile can be compared across cosmic time. Because light from distant galaxies left long ago, surveys at different redshifts provide snapshots from different stages of structure growth. The void population becomes a time sequence assembled from separate regions rather than one object watched for billions of years. Weak lensing, redshift space distortions, and geometry can then be measured on overlapping samples. Agreement among them strengthens the cosmological interpretation. Disagreement can expose an incorrect model, an unrecognized systematic, or a poor connection between galaxies and dark matter. Boötes cannot provide this statistical power by itself. It provides the historical demonstration that underdensity is observable and consequential. The future belongs to the population. This is why wide surveys matter. The Nancy Grace Roman Space Telescope is designed to map large areas of the universe with high-resolution infrared imaging and spectroscopy. Simulations of a potential wide survey indicate that it could identify tens of thousands of cosmic voids, including structures far smaller than Boötes, while tracing their surrounding galaxies with a density the early redshift pioneers could not approach. Roman will not photograph darkness as an object. It will map enough galaxies to reconstruct where the deficits lie. The contrast with the original discovery is extraordinary. Kirshner and his colleagues built the first case from hundreds of redshifts obtained through narrow fields. Future surveys work with millions of galaxies across enormous volumes, producing populations in which the rare tail can be measured rather than guessed. The same missing galaxy method has become a precision program. A gap once challenged cosmology because the comparison sample was too small. A vast catalogue of gaps may test cosmology because the comparison sample becomes large enough. Boötes begins this transformation in miniature. First, a blank interval appears. Then additional sightlines give it scale. Radio observations reveal hidden gas-rich systems. A molecular map shows a rotating galaxy evolving inside the underdensity. Simulations place large voids within a statistical population. Matched surveys turn their shapes and motions into tests of gravity and expansion. The anomaly does not vanish. It changes jobs. At discovery, it pressures the model. After explanation, it becomes an instrument for measuring the model more precisely. That is one of science's most productive reversals. A structure does not need to overthrow a theory to transform a field. It can force better surveys, clearer definitions, larger simulations, and sharper predictions. The Boötes Void did all of that. And the future measurements will not ask whether it contains a hidden monster. They will ask how matter flows around low-density basins, how dark matter traces their interiors, how the average shape responds to cosmic geometry, and whether the rarest members of the population occur at the expected rate. Those questions sound calmer than the original shock. They are capable of reaching farther. A portal would tell us about one extraordinary place. A population of voids can tell us how the entire universe grows. The region that once looked too large for cosmology has become a prototype for testing cosmology. That leaves the title's final question. Why does understanding the Boötes Void make it more disturbing rather than less? The answer requires 4 final distinctions. First, what is it? The Boötes Void is a vast, underdense region, reconstructed from the 3-dimensional distribution of galaxies. It is not a black sphere visible against the sky. It is not a hole in space-time. It is not absolutely empty. Its reality lies in statistics and geography. Across a broad range of positions and distances, the density of bright galaxies falls far below the surrounding average. Later observations reveal smaller systems and gas-bearing groups within it, but they do not erase the large-scale deficit. Second, how did it form? A slight matter shortage existed in the early density field. Neighbouring overdensities attracted material more effectively. Walls, filaments, and clusters grew richer. The underdense volume expanded faster relative to the average. Its matter became more diluted, and fewer dark matter halos reached the masses needed to host luminous galaxies. No completed galactic civilization was swept away. No mature cosmic city was evacuated. The neighbourhood was sparsely built from the beginning. Third, does it break cosmology? Not on present evidence. Modern lambda CDM simulations naturally produce large populations of voids, including rare structures approaching the historical Boötes scale. Exact comparisons depend on tracer selection, boundary rules, redshift distortions, cosmological parameters, and matched mock catalogues. No robust population-level incompatibility has been demonstrated. Boötes is historically anomalous because it exceeded early expectations. It is observationally extreme because of its scale and low galaxy density. It is not presently established as a structure forbidden by the standard model. Fourth, why is it disturbing? Because the universe did not fail there. The universe succeeded. Every familiar law remained active. Gravity attracted matter. Gas followed dark matter wells. Stars formed wherever local conditions allowed. Galaxies rotated. Cosmic expansion continued. Those ordinary processes distributed matter so unevenly that one region became famous for what almost never happened inside it. The Boötes Void is not a wound in the cosmic web. It is one of the shapes the web naturally takes. That is harder to dismiss than a monster. A monster can be located. An explosion can be dated. A black hole can be measured. A portal, if one existed, would possess a boundary. Boötes offers no single culprit. Its cause is the patient amplification of difference. A little less matter at the beginning, a little more gravitational success elsewhere, billions of years in which one region falls behind while surrounding structures become brighter and more connected. Eventually, the shortage itself acquires scale, history, internal anatomy, and influence. Human intuition expects structures to be made from presence. A mountain is rock. A storm is moving air and water. A galaxy is stars, gas, dust, and dark matter. Boötes belongs to another category, a structure defined primarily by deficit, not nothingness, lessness. Less matter than average, fewer massive halos, fewer bright galaxies, fewer rich interactions, longer separations between the systems that remain. There is also a moral temptation in the way people describe cosmic emptiness. We often imagine that a sparse place is unfinished, defective, or less real than a crowded one. The cosmic web offers no support for that hierarchy. Voids and clusters arise together. Remove the underdense regions from the description, and the web itself loses its shape. The void is not merely the distance between structures. Its expansion influences the motion of the structures around it. Its matter deficit affects light passing through it. Its galaxy population records a distinct formation environment. Its size distribution responds to cosmology. Absence has consequences. That is why Boötes can be called a structure, without pretending that nothingness is a substance. A valley is partly defined by the surrounding high ground, yet the valley has a shape, a drainage pattern, a climate, and a history. The lower elevation is not an object placed inside it. It is a relational property with physical effects. Boötes is a cosmic version of that logic. The deficit exists relative to the mean density and the surrounding web, but its evolution is real. Once this is understood, the void no longer seems like blank background. It becomes negative architecture, a form traced by what gathered elsewhere and by what remained too diffuse to shine brightly. This is why the distinction between absolute emptiness and underdensity does not weaken the title. Absolute nothingness would be conceptually simple. There would be nothing to explain inside it. Boötes contains enough matter to preserve a history, but not enough to develop like an average region. It contains galaxies capable of forming stars, yet too few of them to erase the surrounding isolation. It contains local groups, without containing the normal large-scale network of rich environments. It contains dark matter, while lacking many of the highest peaks that would have become clusters. The void is active enough to be physical, and sparse enough to feel impossible. CG 910 captures that contradiction better than any clean black illustration. Its molecular disk rotates. Its cold gas follows ordered motion. Stars continue to appear from clouds whose chemistry and gravity are not exotic. Zoom outward, and the environment changes the meaning of the same galaxy. On the scale of its disk, CG 910 is a complete world. On the scale of Boötes, it is one faint event inside a giant shortage. The science has removed the wrong fears. The void is not approaching Earth. It does not threaten to expand through the universe like a consuming darkness. It contains no known object capable of erasing nearby galaxies. What remains is not danger in the ordinary sense. It is a limit placed on human intuition. We evolved among surfaces, distances, and times that can be crossed. Even an ocean has an opposite shore. Even a lifetime contains events that can answer one another. A region hundreds of millions of light-years across belongs to a different order of separation. Its scale converts communication into ancient evidence. It allows entire galaxies to exist within a wider environment so sparse that their light may travel for ages before reaching another major concentration. And still the region is only one cell within a far larger web. The mind must hold both truths at once. Boötes is incomprehensibly large by human standards. Cosmologically, it is one natural consequence of a much greater structure. Understanding the mechanism does not make the image smaller. It removes the fantasy and leaves the scale intact. There is no hidden event to reverse, no missing population waiting to be found in ordinary light, no dramatic failure that will restore the expected galaxies once corrected. The shortage is the history. The absence is the structure. The science can now explain it. The science cannot make it feel small. Return, then, to one galaxy inside the void. CG 910 continues to rotate. Stars cross its disk. Cold molecular gas follows ordered orbits. Diffuse atomic hydrogen extends through the system. Local gravity gives the galaxy a complete internal world. Nothing in that motion announces a void. A planet there, if one exists, might turn beneath an abundant sky. Nearby stars could fill the darkness. The galaxy's plane might appear as a broad river of light. Dust lanes could divide it. Stellar nurseries could glow at the edges of molecular clouds. No observer standing beneath that sky would feel a physical emptiness pressing inward. The view has to widen. The planet becomes invisible. Individual stars merge into the galactic disk. The disk contracts until its spiral structure can no longer be seen. CG 910 becomes one point. A few other systems appear across the surrounding volume. Some belong to pairs. Some occupy weak local groups. Their existence matters, but the distances between the brighter concentrations grow. Move farther out. The local neighbourhood fades into the larger deficit. Massive clusters fail to appear. Filaments become thin and incomplete. The points that remain no longer form the dense patterns familiar from richer regions. Only at this scale does the Boötes Void reveal itself. The void does not replace the galaxy's local abundance. It surrounds that abundance with scarcity. This is why an inhabitant could live inside a famous void without seeing a black hole in the sky. Voids are not visual objects from within. They emerge from patient measurement, spectra gathered from many directions, distances reconstructed, galaxies plotted in 3 dimensions, expected populations compared with the ones that actually appear. The map knows what the eye cannot. From Earth, the same principle applies. We do not look toward Boötes and see a circular darkness. Foreground stars remain. Galaxies in front of and behind the underdensity overlap in the flat sky. Only redshift separates the layers and exposes the missing middle. A void is an achievement of perspective. It exists physically, but it becomes recognizable only when the view expands beyond any local scene. Pull back again. CG 910 is now too faint to distinguish. The known radio galaxies, molecular disks, companions, and small groups merge into a sparse set of tracers. Their individual stories disappear into the census. Farther still, the surrounding cosmic web begins to glow. Walls of galaxies rise around the underdensity. Filaments stretch toward denser knots. Clusters gather where several strands meet. They do not form a perfect shell, but together they mark the distant return of cosmic abundance. The void takes shape through contrast. Light defines the darkness. Concentration defines the shortage. The regions where gravity gathered matter most successfully outline the region where it gathered less. Nothing in this view is static. Galaxies move. Matter continues to flow. The universe expands. The boundaries evolve. Over immense spans of time, voids grow relative to the structures around them, and the difference between crowded and sparse becomes more pronounced. Boötes is therefore not a frozen cavity. It is one frame from a continuing history. That history began when the density difference was barely present. It passed through ages in which the first halos formed, the first stars ignited, and the cosmic web sharpened. It continues now in gas-rich galaxies whose disks turn within the low-density interior. The void connects the earliest measurable unevenness to the present distribution of galaxies. A gap on a graph becomes a record of cosmic evolution. The first astronomers who saw that gap could not know every detail that later observations would add. They did not know about the full, small-scale HI population in the selected fields. They could not map the molecular gas of CG910. Their simulations could not yet produce vast, well-resolved populations for comparison. But the missing galaxies were real enough to force the next question. The zoom-out also changes time. The light from one side of the region did not leave at exactly the same cosmic moment as the light from the other side. A three-dimensional map corrects distances as carefully as possible, but every observation still arrives through a light cone. Farther structures are seen deeper in the past. For a nearby void, this difference is modest compared with the age of the universe. Yet across hundreds of millions of light-years, it is not zero. The complete image is never a photograph taken everywhere at once. It is a reconstruction of an evolving structure from delayed messages. That fact makes the final view quieter. The galaxies around Boötes do not know one another in a shared present. Gravity propagates through spacetime. Light carries old information. The web is connected physically, but no observer can step outside it and see every component as it is now. Human beings create the wide view by combining measurements, models, and patience. The void becomes visible because generations of observers add layers the local eye cannot possess. Optical spectra, radio lines, simulations, molecular maps, and statistical catalogues. The final image is therefore both natural and constructed. The underdensity exists without us. Its recognizable shape is an achievement of evidence. That is how scientific anomalies do their best work. They interrupt confidence. Some disappear when the measurement improves. Some expose an error. Some require a new theory. Others, like Boötes, survive as real structures while changing category. What first seemed almost incompatible with the universe becomes an extreme expression of how the universe is built. The discovery still matters because the surprise was productive. It expanded the map. It sharpened the model. It changed emptiness from background into subject. And it left us with an image no equation can entirely domesticate. One galaxy turns inside the underdensity. Its stars do not feel abandoned. Its gas does not understand isolation. Gravity does not know that human beings have given the surrounding region a name. Only the wider map knows where the galaxy is. Far beyond its disk, the nearest rich structures remain separated by distances that light itself crosses on geological and evolutionary timescales. Beyond them, the web continues into regions so vast that Boötes becomes one dark cell among many. Yet for the systems inside it, the local consequence remains specific. Fewer massive neighbours, fewer crowded intersections, a cosmic address defined by the things that failed to assemble nearby. The universe did not remove those neighbours after the fact. It never built most of them there. That is the final correction, and the final disturbance. The Boötes void is not defined by absolute nothingness. It is defined by how lonely the things inside it have become.